Imagine looking at a piece of metal, a grain of salt, or even a complex pharmaceutical powder. To the naked eye, they just look like solid, everyday objects. But deep down at the microscopic level, there is this hidden, incredibly organized language of atoms. It's literally a structural code that defines everything about how that material behaves in the real world. Now, obviously, our eyes can't read this microscopic language, but today we're going to explore the ultimate scientific decoder ring. X-ray diffraction, or XRD for short. It's this brilliant technique that lets us bounce light off atoms to map out their exact arrangements. Here is our roadmap for today's explainer. First, we'll cover the 5 steps of XRD. Second, unlocking Bragg's law. Third, reading the XRD pattern. Fourth, sizing up crystallites. And finally, number 5, what XRD actually tells us. All right, let's jump right into section 1, the 5 steps of XRD. So before we can even think about analyzing any data, we need to track the actual chronological journey of an X-ray. And this whole process breaks down into 5 distinct steps. It kicks off with generating the X-rays at the source. Next, that beam is directed as an incident beam straight onto our sample. Step 3 is really where the magic happens. That's the diffraction itself, where the X-rays actually scatter off the atomic planes. Step 4 is capturing those scattered rays with a detector. And finally, step 5 is translating all that detection data into a visible, readable XRD pattern. Let's actually visualize this physical setup. It all starts with the X-ray tube, which very often uses copper K-alpha radiation, acting as our monochromatic X-ray source. And monochromatic just means we're using one single, highly specific wavelength. Okay, so that collimated focused incident beam travels and hits our crystalline sample. And the second it strikes the sample, those X-rays scatter off the repeating planes of atoms. We then have a detector mounted on a rotating arm, which is called a goniometer. As the incident beam comes in at a specific angle, called theta, the detector sweeps along an outside arc, capturing the diffracted X-rays at an angle of 2 theta. That detection feeds straight into a computer, giving us our final intensity graph. Moving right along to section 2, unlocking Bragg's law. Okay, so we know the beam hits the sample and bounces into a detector. But you might be wondering, why does that give us a sharp, spiky graph instead of just a random blur of scattered light? Well, the fundamental secret of XRD is that it doesn't just bounce light around randomly. It relies entirely on a phenomenon called constructive interference. When X-rays hit the different layers of atoms in a crystal, the rays bounce back. If the waves of those bouncing X-rays line up perfectly, we're talking peak to peak and trough to trough, they amplify each other. This perfect syncing creates a maximum signal intensity, which the detector picks up as a really sharp spike. Now, if they don't line up, they just cancel each other out, and the detector sees absolutely nothing. This constructive interference is literally the foundational key point of the entire XRD process. And that perfect wave syncing brings us right to this mathematically elegant equation, Bragg's law. Formulated by Lawrence Bragg and his father, William Henry Bragg, this is the exact mathematical translation of the constructive interference we just talked about. Let's break down these specific variables so we know exactly what inputs we're working with here. The lowercase n is just an integer representing the order of diffraction. The Greek letter lambda, that represents the specific wavelength of the X-ray we're firing from our tube. Then there's d, this is the big prize. That is the interplanar spacing, or the actual physical distance between the layers of atoms in our crystal. And finally, theta is the Bragg angle, which is the angle our incident beam hits the sample. Now, because we already know the wavelength of our X-ray machine, and we know the angle theta where the detector found a strong signal, we can use this little equation to easily solve for d. And boom, we've just revealed the hidden atomic layout of the material. Which brings us to section 3, reading the XRD pattern. So we have the machine and we have the math, but how do we decode the actual graph? On an XRD pattern, the x-axis is our 2 theta angle, and the y-axis is the intensity of the X-rays hitting the detector. Each sharp peak corresponds to a specific set of crystal planes, often labeled with Miller indices, H, K, and L. By noting the exact 2 theta position of a peak, we just plug that into Bragg's law to find d, our interplanar spacing. Plus, the height or the intensity of the peak actually tells us about the relative amount of that specific phase or its orientation. And the best part? You don't have to calculate every single material from scratch. In the real world, scientists take this generated pattern and just cross-reference it against massive standard databases like the ICDD or JCPDS.
If your pattern perfectly matches the database pattern for table salt, well, you've got table salt.
Next up, Section 4, Sizing Up Crystallites. The position of the peaks tells us what the material is and how its atoms are spaced, right? But there's another incredible layer of information hidden in the graph, because not all peaks are created equal. When we look closely at a peak, we measure something called the full width at half maximum, or FWHM. Basically, it's just how wide the peak is at exactly half of its total height. If you have a large, highly ordered crystallite, you'll get a very small FWHM, meaning the peak is tall, sharp, and skinny. On the flip side, if you've got a very small crystallite, or maybe a material with structural strain, defects, or amorphous regions, you get a large FWHM. That gives you a short, wide, broad peak.
So, if you take away one golden rule of XRD interpretation today, let it be this. Peak broadening is inversely proportional to crystallite size. The wider the peak on your screen, the smaller the actual crystallite is under the microscope. It's this perfectly inverse relationship that allows us to measure things on the nanoscale simply by looking at how fat a line is on a graph. Pretty amazing, right? And just like Bragg's law gave us the math for spacing, the Debye-Scherrer equation gives us the specific math we need to calculate that crystallite size. Here, capital D is the crystallite size we want to find. We calculate it by taking a shape factor K, which is usually around 0.9, multiplying it by our X-ray wavelength, lambda, and then dividing all of that by the product of beta and the cosine of our Bragg angle, theta. Beta is the really crucial part here. It's that FWHM, the width of the peak we just talked about, measured in radians. Plug those numbers in, and you can legitimately calculate crystal sizes down to the nanometer.
Finally, let's wrap up with Section 5, what XRD tells us.
We've gone incredibly deep into the weeds of atomic bouncing, constructive interference, and nanometer calculations. Let's just take a breath and zoom back out to the big picture to show the real-world utility of all this physics. When you combine the peak positions, their intensities, and their shapes, you get an unbelievably rich diagnostic profile. From just a single XRD scan, we gain 6 massive pieces of information. We can identify the phase impurity of a material. We can map the entire crystal structure and lattice parameters. We measure the interplanar spacing. We calculate the nanoscale crystallite size. We can actually detect if the atomic lattice is under physical strain or if it has internal defects. And lastly, we can determine the overall degree of crystallinity versus amorphous content. This is exactly why XRD is viewed as an absolute game changer and one of the most indispensable techniques in chemistry and materials science today. So there you have it. You are now equipped with the fundamental understanding of how we bounce light off unseen atoms and translate their echoes into a blueprint of reality. It's honestly like having microscopic X-ray vision. So my question to you is this. Now that you know how to read the structural code of the universe, if you could put any material on that goniometer right now, what atomic fingerprint would you decode first?